This playlist deals with some aspects of Eurocode 2 version 2023, and watch this playlist for further selected topics. It is about clause 9, and it deals with serviceability limit state, about the minimum reinforcement to avoid yielding, part 3. In chapter 9.22, the minimum reinforcement to avoid yielding is valid for the crack width when the crack width is not specified and the steel stress is equal to the yield stress of the reinforcement. It states that instead of using formula 9.2, 9.3 and 9.4, it is also allowed to apply the principle of 9221. And the principle of 9221 is that the required minimum area of reinforcement to avoid yielding shall be calculated by applying the principle that reinforcements working at the characteristic yield stress should balance the moment that cracks the section, acting together with the relevant axial force NED. Remember, 9.2 is for bending, 9.3 for tension, and 9.4 for the combination of the two. So we will apply this principle in SLS characteristics, and we will calculate the cracking bending moment, which is equal to W times the stress at the utmost fiber. This cracking bending moment is equal to the applied bending moment and is equal to eccentricity E0 times the total normal external axial force. NED in this formula, I'm using them all. I also use NSD instead of NED, but it's the same. And W is the section modulus of the section, which is a function of the reinforcement and the compressive height. We now look at a simple section of concrete subjected to a bending moment, and it creates a compressive area and with a depth of X. The geometric or the point of gravity of the section, we assume it is midsection at h/2. The compressive force in the steel AS2 is equal to NS2. The compressive force of the concrete is NC, and the total external force is NSD or NED with an eccentricity E0, and the tensile force in the reinforcement is NS1, and it's acting on a distance of D1 and a distance of D2. So this is all well known. We can now use a translation equilibrium, which is easy. This one, just pay attention. I'm not using the sign agreement of NED is positive for tension and negative for compression. Here I'm using the symbols as it is acting on this figure. So if NSD is working in this direction, then it's compression. If it's working in this direction, then it is tension. But it's just a detail of this formula. So you have a translation equilibrium and a rotation equilibrium. So we have two equations. Now we can also see that the total compressive force is equal to the to this formula, to the triangle, to the surface of the triangle. The tensile force in the reinforcement is, of course, the AS1 times this stress in the reinforcement. The same acts for NS2. You see, I'm not using signs here. Huh? And the stress in the reinforcement can easily be calculated with this simple formula. We will now solve the two or now you can solve the two equilibrium equations for X after substituting, of course, of all those different values that we've calculated here. You substitute it, and then you can have X. And when you have X, you can substitute it in this, and you can calculate the AS1, which is equal to then to AS minimum W1, and the same is for AS2. Now this is quite we can simplify the formulation. For instance, for pure bending, then NED is 0, and the phi factor in SLS characteristic is 0. There is no creep taken into account, and we assume symmetrical reinforcement. Now, in most cases, the reinforcement is symmetrical because you need minimum reinforcement at the top and the bottom of the section. So that's an assumption which is acceptable. Then the formulas become as follows. XE is the compression height for the uncracked section because you are calculating here the cracking bending moment. And this compression height for uncracked section is a function of the width and depth of the section and the position of the reinforcement. EE is the second moment of area of uncracked section, and it's given by this formula. And then we assume, of course, D1 is equal to D2 and is given by this formula, assuming that there is only one layer of reinforcement and only use of one diameter, no different diameters in the same layer. Then we can calculate ASW1 is equal to ASW2. It's just the bending moment divided by Z, the lever arm, divided by the yield stress of the reinforcement. And Z is equal to D minus X over 3, and D is H minus D1. Then X is the compression height for the cracked section. It's equal to this formula. And alpha is the ratio of the modulus of elasticity of the concrete divided by the modulus of elasticity of the steel divided by the mean modulus of elasticity of the concrete multiplied by 1 plus phi. Phi is here 0, so it equals to ES divided by ECM. And ECM is for quartzite, this formulation, and FCTM or FCT effective is equal to FCTM is equal to 0.3 FCK to the power 2/3. I'm assuming that FCK is smaller than C50. Now we can neglect the contribution of the reinforcement to the cracking moment. You make a small error, but it's on the safe side. And we assume a symmetrical reinforcement. We obtain, assuming a symmetrical reinforcement, we obtain a more simplified formulation. So the minimum reinforcement is then the cracking bending moment divided by Z over the yield stress of the steel, and the lever arm Z can be estimated as 0.8 times the depth of the section, which is for slabs, and 0.9 times the depth, which is for beams. It's just an approximation. And then you will see that, or we can calculate the cracking bending moment as the same formula, or it's the formula for a section without reinforcement in it. So it's a uniform section, so it's a known formula. It's much simpler than the previous one. When we combine this, then you will see that the minimum reinforcement is given by 0.21 AC times this term for slabs and 0.19 for beams. So in practice, you can use for slabs and beams just 0.1 times AC times FCTM divided by FAK. So this is a much more simplified method to calculate minimum reinforcement to avoid yielding. When we can compare that now with formulation 9.2 of the Eurocode 2 2023, and we see that it's 0.2 kH. This is the same as we got here. So we have 0.2 KH, and KH is between 0.5 and 0.8. So if you take the larger value of 0.8, then you will see that it's 0.16 times this formulation. So 0.16, we are with this new formula 0.9, 0.21, it's bigger than the 0.16, so we are on the safe side. So if you want to gain some time and some simplicity in your formulation, you can easily use this formula instead of the more complicated ones. And it's on the safe side. Clause 4 says that beams with a downstem depth of more than 600 millimeters, where the main tension reinforcement is concentrated at the most tensioned fiber, which in most cases so, should be provided with additional longitudinal reinforcement given by formula 9.7 at the spacing not exceeding 300 millimeters, control cracking on the side faces of the beam. This reinforcement should be evenly distributed between the level of the reinforcement layer closest to the most tensioned fiber and the neutral axis. So this means that when having a rectangular section and X is the compression height, this is the neutral axis, then you should add additional tensile reinforcement. It's the red one, additional tensile reinforcement between the neutral axis and on a distance A1, which is 150 millimeters from the most tensile side. In this area, you must provide a minimum reinforcement equal to AS web, given to this formula. And we will now take a simple example, a beam of 1 meter by 300 millimeters, concrete grade 30, and the effective depth is, for instance, 900 millimeters. What is X? This clause does not say in which ultimate limit state you have to calculate it. So we don't know what is the X. It's not clear. It certainly is not the X under an external load, under an external load from different load cases. So it should be a specific load case in a specific ultimate limit state, but it's not stated in clause 4. But now we can assume, because it's SLS, so we can say it will not be more than 0.2 times the height or the depth of the beam. So we estimate that 200 millimeters. It will be around that. Then applying this formula, we arrive at 191 square millimeters or 4 diameters 8. And that are the 4 red dots. Don't confuse this reinforcement with skin reinforcement. Skin reinforcement is for high depth beams, but then the skin reinforcement is put outside of the reinforcement outside the stirrups. Sorry. So skin reinforcement is put outside the stirrup, and this is about additional tensile force reinforcement to avoid yielding. Amazing is that it's valid as from 600 millimeters onwards. So that's most beams are 600 millimeters depth, have a depth of 600 millimeters or more.